Great. So yeah, welcome everyone to an Earth Mover webinar. It's my pleasure to introduce our presenter for today. So I'm Ryan, I'm the CEO of Earth Mover. And today we're lucky to have a presentation from Emma Marshall. So Emma is a PhD student in the cryosphere lab in the geography department at the University of Utah. And so in her normal work, she's working with remote sensing data, using it to study glacier variability in high mountain Asia. So along the way, Emma has become an open source contributor, working on Xarray and doing a lot of great work around education, around best practices for geospatial data science. And that's how we got to know Emma. And we're fortunate that Emma has spent the summer working at Earth Mover as a developer relations intern, where she's contributed across the company, both to our code base, our documentation, and has done a lot of great work on providing sort of educational material and tutorials like the one you're going to see today. So really excited to have Emma here presenting. And Emma, I'll hand it over to you to take over.
Awesome. Thanks, Ryan. And thank you, everyone, for being here today. Vector data cubes in Xarray and Zarr are a really exciting development, so I'm glad for the opportunity to be here today to talk with you all about them. Okay, a little bit of housekeeping before I get going. Please stay on mute during the presentation. If you have a question during the talk, you can use the Q&A tool in the bottom right corner of the Google Meet. And then after the Q&A, after the talk, we'll have a Q&A session, and you can also raise your hand during that using the hand raise feature. Here's an agenda for what I'm going to be talking about today. I'll first introduce myself and Earth Mover and talk a bit about what we're building at Earth Mover. Then I'll talk about vector data cubes, both what they are and why we're so excited about them, before moving into a vector data cube demo. So a little bit about me. As Ryan said, I this past summer was a developer relations intern at Earth Mover. And outside of that, I'm a PhD student in the geography department at the University of Utah, where my research involves using satellite imagery to better understand recent variability of Himalayan glaciers and connections to climate. So to go into a little bit more detail on that, first, what are glaciers? Glaciers are large bodies of ice and other materials, and you can think of them like large frozen rivers that are flowing down mountains. They form, expand, and retreat in response to climate conditions. So looking at the evidence of past glacial advances and retreats is a really important indicator about the past of our climate system. In high mountain Asia and all over the world, mountain glaciers, this characterization fits for mountain glaciers all over the world, but in high mountain Asia, glaciers are very important seasonal water resources, as well as potential sources of geologic hazard and contributors to global sea level rise. So in the Indian subcontinent, over 500 million people live in downstream catchment areas from glaciarized area. And this means that they're very impacted by both glacier runoff and hazards associated with glaciers. Seasonal glacier runoff supports functions such as hydropower generation, irrigation, municipal water uses, and biodiversity and ecosystem services, as well as there's a potential risk for glacial lake outburst flood events and landslides associated with glacier retreat. We know that Himalayan glaciers have been losing mass for over a century, and a number of recent studies have shown that rates of mass loss in recent decades have accelerated, which makes understanding the trajectories of these glaciers in a warming world very critical to the development of robust and effective mitigation strategies. Back to Earth Mover. Earth Mover is a public benefit corporation whose mission statement is to empower people to use scientific data to solve humanity's greatest challenges. Earth Mover was founded by Ryan Abernathy and Joe Hammond, who are both climate scientists and leaders in the open source community. And the Earth Mover team has scientists, open source community leaders, and experienced engineers who've built in production grade infrastructure for data intensive workflows at a number of companies. At Earth Mover, we're building Arraylake. Arraylake is a software layer that sits in between you and your team over here on the left and your data that lives in object storage on the right. And Arraylake really does two things. It implements a catalog that lets you query and understand your data by making use of your metadata, and it adds safety through features such as access controls, ACID transactions, and data versioning. These allow you and your team to collaborate safely on common data sets. So you can really think of Arraylake as a database and a data lake for Zarr data, though it works with all types of array data. And we're going to see later on that we can also work with different types of data in Arraylake. Arraylake is built to be complementary to and tightly coupled to open source software packages, mainly Xarray and Zarr. Xarray is a Python package for working with multidimensional labeled array datasets in Python. It's based on the netcdf data model, and it has an API that supports indexing, selection, computation, and visualization of data using those labeled dimensions. So we think of Xarray as kind of our query interface. If we're wanting to go into a data set and extract a value, perform a computation, make a visualization, we're using Xarray to do that. If Xarray is our query interface, Zarr is our storage interface. Zarr is a storage format with an associated Python API that's built for chunked, compressed, multidimensional data. It's highly scalable and it's cloud native, so we see it widely used across all cloud object stores, including S3 and Google Cloud Storage. And before I move on, I want to just take a moment to acknowledge a lot of other groups and projects within the open source community whose work was really pivotal to the development of vector data cubes in Xarray and to the demonstration that I'm going to show today. So I'm going to be using data from the Overture Maps Foundation and Weatherbench 2. In terms of software, Xvec is the new package in the Xarray ecosystem that really brings this vector data cube functionality to Xarray. So I'm going to talk about that in a lot more detail later on. We're also going to be using tooling from CF-Xarray, which is another package in the Xarray ecosystem that helps you connect your CF metadata with your Xarray data structures to incorporate them into your analysis. Xarray and Zarr I've already talked about. GeoPandas is a Python package for working with vector data in a data frame format in memory. We're going to use DuckDB to query the Overture Maps data set rather than having to read in an entire massive data set. And we're working with shapely geometries in memory and GeoParquet files in object storage. And I want to just make a special shout out to the Pangeo community, which is a place where a lot of development, discussion, iteration on these tools and others have occurred. Okay, getting into geospatial data, I'm sure many people are here are familiar with the traditional representations of geospatial data, but as a brief overview, before we dive in more into this, I want to just kind of lay out an example and description of raster and vector data. So we could go way more into the details on this, but very simply, raster data is data that has pixels, like satellite imagery, model output data, gridded data sets, things like that. Vector data describes real-world features such as roads, rivers. This is an image of glacier outlines, flood extents, buildings, cities, things like that, as points, lines, and polygons. So these are kind of two of our main building blocks here. And just a note on how I use vector and raster data in my research, and I'm sure this is relatable to a lot of folks out there. In my research, I am trying to answer questions about glaciers, and I use different types of data to do that. I have ice velocity time series that are derived from satellite image pairs. These are raster data cubes. But I have so those are very large cubes covering an entire region, and I'm really only interested in the velocities at certain areas. So I have glacier outlines, center lines, and points represented by polygons, lines, and strings as my vector data there. And what I'm really interested in is the behavior of the raster data within these complicated vector geometries. So it really motivates a lot of the kind of need for a way to combine raster data and vector data, and the excitement around vector data cubes. To go back to raster and vector data, so these are the same images that I just showed, but I want to focus in a little bit more on how we represent these data types. And the main distinction here, there's a lot going on in this slide, but the main thing that I want to highlight is that we tend to represent raster data as multidimensional cubes and vector data as multidimensional data frames. So I have the Sentinel-2 image and the glacier polygons shown here, and then I have schematics of what would be kind of a typical representation of this data that we might work with as analysts. So the Sentinel-2 image, this is a single time series. You could imagine this as a single slice of this three-dimensional cube. We call it a pancake. And then in turn for the glacier outlines, we have a number of glaciers shown here, and they would be represented in a table format like this, where each row is a glacier. We have a geometry containing a shapely polygon that describes the outline of the glacier, and then we have attribute data about the glacier. And a couple things I want to highlight here. Raster data cubes support multidimensional data, and really they support multidimensional indexing. So I'm going to be mentioning indexing a lot, and so I just want to briefly kind of explain what I mean there. It can get a little bit jargony, but when I say we have a multidimensional index or a spatially aware index, that's really talking about how we interact with the data object and how we can kind of move into it, pinpoint the value that we want, and get it back. Indexes help us know how to do that given a data structure. So for raster data cubes, we have indexes for different dimensions. However, they're not spatially aware indexes. So they cannot perform functionality like finding all points within a buffer of a certain point, or masking and filtering. In turn, vector data frames are kind of locked into, they have one functional dimension, but they do have spatially aware indexes. So they don't support multidimensional data, but they overtly, but they do have spatially aware indexes that allow us to perform really powerful operations. In addition, vector geometries can be directly written to tabular file formats, whereas with array-based file formats, like those that we use for data cubes, the vector geometries traditionally can't be directly written to those file formats. So we've gone through kind of a little bit about what we have in raster data cubes and vector data frames and the strengths and limitations of each. Now I want to kind of start motivating the situation where we want to be combining data from, or combining kind of functionality from both of these models. So let's return to the example of having glacier polygons shown here. And we have a data frame describing this data set. You can see we have a row for every glacier, and then we have attribute data about that glacier. We have something like an ID, some elevation information, an area measurement, and then an average velocity estimate. So this is a really great way of representing this data. However, what do we do when we get a new velocity estimate or a new area estimate? Maybe a lot of time has passed. We have a new observation. We want to start adding that to this data frame, but it's not immediately clear how we ought to do that. This data frame structure doesn't really have a built-in way of doing this. And if we are kind of explicit about what we're doing when we are adding new time steps to this data frame, what we're really doing is creating a new dimension, a time dimension, that exists in addition to this geometry dimension. There are definitely ways to coerce multidimensional data into a data frame format, such as wide form or long form, but these will involve duplicating data along either the row or the column dimension, and it's going to produce inefficiencies and awkwardness when you try to query that data. And ultimately, where that awkwardness and kind of cumbersomeness comes from is that the data frame structure is not really a good match for the physical structure of our data set. And that's because, as I said, our data is multidimensional, and what we really want is a multidimensional structure to represent it. And that's what brings us to vector data cubes. So the definition of vector data cubes is a data cube where at least one dimension is an array of vector geometries. So when we are working with multidimensional data sets that have a spatial component, a vector data cube is really a data structure that much better matches the physical structure of the data set compared to either a raster data cube or a vector data frame. And I try to show that with this schematic here. So this is the same glacier example with the data frame structure on the left and how we would start to represent time series data within that data structure. And you can see that we're duplicating all of these observations by adding rows for time. In contrast, if we represent this data as a data cube, we can represent all of the data that's shown in the data frame in this data cube without duplicating data and by simply adding a time dimension. This lets us kind of set up a data model that is more streamlined. It's more intuitive, and it's going to be more streamlined for our analysis. For anyone interested in a really great and much more comprehensive talk about vector data cubes and vector data cubes in Python, I really highly recommend Martin Fleischmann's 2023 talk at EuroPython on the subject. Great, so I think we've kind of motivated why we would want to work with vector data cubes in Xarray with vector data cubes. But the situation is that we have not been able to do that in Xarray thus far, and that's because a number of adjustments need to be made to make the existing kind of tooling for working with raster data cubes functional for vector data cubes as well. And that brings us to Xvec. Xvec is a new package in the Python ecosystem. This is a really exciting development. And with Xvec, you can construct in-memory vector data cubes, perform spatially aware queries with a special index that can understand and apply spatial information, and then you can save vector data cubes to Zarr stores and other array formats. So I just want to take a minute and acknowledge and shout out all of the Xvec developers. This is a project that came together with work from many members across the open source community. And as a user and analyst and learner, this is one of those developments that I think will really transform my kind of working experience and that of others as well. This is a really great contribution to the community. Okay, now I want to get into building a vector data cube. I'm going to motivate this by considering a question that we'd like to ask and then how we would answer it. So this is a question that I think is probably pretty representative of a lot of workflows that seek to combine raster and vector data. And that's, how do atmospheric variables such as temperature and near surface wind speeds vary at wind power generation sites in a given country? We're going to use Germany in this example, but you could fill in your own location data. And to answer this question, we're going to need some different types of data. We are going to need vector data that describes the locations of the points that we're interested in. And we're going to need raster data that has that describes the atmospheric variables that we're interested in. For the raster data, we're going to be using the ERA5 atmospheric reanalysis dataset. This is a dataset that has 30+ variables describing the atmosphere for going back from 1960 or so to 2022. So this is a massive global dataset that can be quite complex and kind of computationally heavy to work with. We're really lucky to be working with the analysis-ready version that's prepared by the WeatherBench 2 project and made publicly available in Google Cloud Storage. For the vector data, we are working with the Overture Maps Foundation Places dataset. This is stored as GeoParquet files in S3 buckets on AWS, and we access this via a DuckDB query. Okay, now I'm going to switch gears and move into a Jupyter Notebook demonstration. Okay, great. So in this Jupyter Notebook, I'm going to set up data that we would use to answer the question that we've just stated. I have some utility functions up here that I'm not going to go through, but I'm gonna be working on this project in Arraylake. So that's just kind of like where we're situating this. You can see that I've connected to our client, and then I've gone to a repo I created called Vector Cube Webinar. We can just take a look at the status of that and see that it is empty. Oh, okay. Actually, here's what we're going to do. This morning, the widgets stopped displaying very well. So what I'm going to do to just show you the data that we are writing and working with is switch over to our app here and show you this is our repo. This is our Arraylake repo, and you can see that it's empty. As we add data to it, I'll switch back over and you can see that. But so we have an empty repo, and let's change that by ingesting some data. So we're going to ingest the GeoParquet data from the Overture Maps Places dataset that I described. So this is just a visual of what we're doing. We're pulling every point from the Overture Maps Places dataset that's located within Germany and is categorized as wind energy. We do that by writing a DuckDB query. It takes several minutes, so I've already run it and I'm not going to run it here, but essentially this function here just executes the DuckDB query and it returns it as a geodata frame, which you can see here. This matches the data frame format that I showed in the examples before, where we have a row for every observation that contains a point geometry and then attribute data about that point. And what I want to emphasize here is that a geodata frame is essentially the simplest form of a vector data cube, which is a one-dimensional vector data cube. As I mentioned before, we can represent all of the information stored in this vector data frame in a one-dimensional vector data cube. And that's what I want to do here. I want to highlight that before Xvec, we could have still coerced this information from the geodata frame into an Xarray data set, but we would have lost the spatial metadata and the spatial, functionality of that data set. With Xvec, we are able to convert this geodata frame into a functional one-dimensional vector data cube. So that's what we'll do right here. This code just brings all of the data from the geodata frame describing wind power plants in Germany into an Xarray data set. So you can see we have a one-dimensional Xarray data set. And what I want to just point out here is that we have an index along this geometry dimension, and it's a pandas index, which is the standard index that all Python objects have. It's inherited from pandas. So this has all of the functionality of a pandas data frame index. It does not have the spatial functionality of a GeoPandas geodata frame index, and that's going to be important. Great, so I'm going to just come over here. Can everyone still see my notebook? Yeah, okay, great, thank you. Okay, great, so I'm going to just come over here and convert this one-dimensional Xarray data set to a 1D vector data cube. And we'll do that by going, see if I'm tempting fate a little bit with the live coding, so we will see how I do. Might make some typos. So we're going to Xvec acts as an accessor to Xarray objects. So we add it to an Xarray object, and then we call a method setGeomIndexes. So this is just going to, we tell Xvec which dimension we want to add a geometric index to, and then we give it coordinate reference system information about that object. So we can just run this and see here that we still have a one-dimensional Xarray data set, but now instead of a pandas index, we have this geometry index here. So this is going to let us perform those spatial queries that are really powerful with vector data. Great, so we've created an in-memory vector data cube, and what I want to show now is that not only can we do that, we can also write that object to Zarr, which, if you remember to the introduction, was not previously possible to write vector geometries to array file formats like Zarr. And this is because of how the geometries are encoded in memory. In memory, we're working with an array of shapely point geometries, and shapely geometries are really powerful for working with in-memory work like this, but they have some higher order structures that are not compatible with array-based file formats like Zarr. So what we do is we need to encode those shapely geometries into a simpler format that Zarr and NetCDF can understand. There are different options with how you could do this, but we are going to encode the shapely geometries as CF geometries. This is from the Climate Forecast Metadata Conventions. And CF geometries essentially just deconstruct shapely geometries into sets of simpler objects. For anyone familiar with GeoArrow, CF geometries are structurally similar to GeoArrow geometries. And I'm going to just encode those geometries here with the help of a Xvec method. So I'm going to say encoded, yes, equals, and I'm going to just call it encode CF. And we can take a look at what this object gives us. Great, so you can see this is similar to the object before, but now we've kind of expanded that geometry dimension. We have now nodes, and we have this geometry container object, which gives us some information describing the relation of the nodes to one another to make those an ultimate point data set. Now that I've encoded those geometries as CF geometries, I can write this object to Zarr. So I will do just like this. So I'm going to write it to the Zarr store associated with our Arraylake repo. We could write this to any Zarr store. An Arraylake repo is just a special type of Zarr store, and this works with any Zarr store you have. You can write a data cube once the geometries are encoded to CF geometries. So we'll just go like this, write that. Great, it looks like it worked. I'm just going to commit those changes so that we can see them reflected. Wrote 1D cube. And let's try this. I don't think it's really going to show us what we want. Okay, so rather than do the tree, we are just going to come over here. And you can see I created this one cube 1D group, and these are all of the arrays that I just wrote to our Zarr store from the vector data cube. Okay, now I want to show that we can read this data back into memory from our Zarr store and end up with ultimately the same object back. This is really critical for vector data cubes being like functional reusable objects in our analyses, is the ability to write them to file and read them back into memory. So let's take a look at that now. I'm just going to read this back in by pointing to the repo, saying to Xarray, and giving it that group. So you can see here that I read this back in, but I still have CF geometries. So I'm just going to encode this back and say vec cube 1D equals vec cube 1D Xvec. Now decode CF. So this is going to go from CF geometries to shapely geometries. Great. And we are back to the one-dimensional data cube that we started with, where we have a geometry dimension made up of an array of shapely points. This is great. This is exactly what we want. Let's just convince ourselves one more time that these objects really are identical. And it's true. Awesome. Okay, we feel good about that. I'm going to pause here and just recap this section, because it might have, I think, on one level, it was relatively simple what we did, but this is actually a really exciting development. And this was not possible even just a couple months ago before some new functionality in Xvec. So I want to just emphasize that with Xvec, it is possible to read in GeoParquet data, convert it to an Xarray dataset with a spatially aware geometric index, and then write that object to Zarr and read it back into memory without losing any of the spatial metadata. So it's a really exciting development, but we still can do so much more. We haven't even really touched on the higher dimensionality objects that were the main motivation for working with vector data cubes in the first place. So in section 2, we'll do that, and we will continue to set up the data to returning to our question and set up data to answer our question. So we're going to build a multidimensional vector data cube by joining raster and vector data. Again, we're going to be using the Era 5 analysis ready dataset from Google Cloud Storage and Weatherbench 2, and then the Overture Maps data that we just created a vector data cube to store. And this is just a schematic of what we're going to do. So we have this entire global Era 5 dataset. It's large, it's way more than we need. And really what we're interested in is these variables only at our set of points. So what we want to do is we want to sample the 3-dimensional raster data cube into a 2-dimensional vector data cube, where we have a time dimension and then a dimension representing each of our points. So let's do that here. I'm first going to read in the raster cube. So I have this URI pointing to the location of the data in Google Cloud Storage, and I'm just going to read it in with a function I defined before, just to make some of this faster. Great, so you can see we have a 3-dimensional raster data cube where we have pandas indexes for each of the 3 dimensions. Next, let's sample the raster data cube to make that 2-dimensional vector data set. We're going to do that using Xvec's extract points method. So we're going to say raster data cube is the object we want to sample. Then we're going to call Xvec extract points. And we're going to give it the geometries that we want it to sample from. So those are the geometries from the vector cube 1D object in the geometry dimension. And then in the raster data cube, we need to tell Xvec where, like, the dimensions that it should be looking over as it samples. So we're just going to tell it that the X coordinates are longitude and the Y coordinates are latitude. And we can take a look at that object. Okay, very cool. So we've gone from that 3-dimensional raster data cube to a 2-dimensional object where one dimension is an array of points, a vector data cube. And if we take a look at the indexes, we have a pandas index still along the time dimension, but then we have this geometry index along the geometry dimension representing our points. So we've worked with this data in memory, but so far all of our computations have been lazy. If we wanted to actually perform, next we want to actually perform some computations. So I would load this into memory. I've already done this because it takes a couple minutes. So we're just going to move forward in the example using that object. And I want to show that we can perform some typical, very popular time series analysis steps with this data set that leverage the dimensional functionality of Xarray while preserving the spatial information of the vector data cube. So let's compute seasonal mean values for our atmospheric variables using Xarray's group by. So we're going to say vector cube 2D group by Xvec cube 2D mem group by time season. And we're just going to tell it what reduction to perform over those groups. Great, so you can see we've collapsed our time dimension to a season dimension that has 4 elements, and we've preserved our spatial dimension here. Next, we can visualize that data. Here's where I want to note one of the kind of rough edges that still exists with Xvec and Xarray, and that's around Xarray's built-in plotting routines. So these still sometimes don't play very nicely with the spatial data in a vector data cube. But the good news is that Xvec implements really easy interoperability with GeoPandas. So we can really smoothly convert from an Xarray dataset to a geodata frame and back, which means that we can use GeoPanda's really excellent visualization tools. So that's what I'll do right here. I want to call that group by object, and I'm just going to convert it to, I'm going to select just a single season. So we'll look at winter. And then I'm going to convert that object to a geodata frame. So I'm going to say Xvec to geodata frame. And then what I really want is GeoPanda's explore method to give us an interactive map. So I'm going to look at the wind variable. If I can spell that. Great. And we'll tell it a bit more information. Okay, cool. Now we have an interactive map where we can see all of our points represented on the map, and then we can see the mean wintertime wind speeds represented in colors. So we can hover over them and see more information about a given point. And we can start to get a kind of an idea of just the spatial relationships in our data set. So I really appreciate that we can so smoothly go from this Xarray object and all of the functionality that that brings us to the spatial plotting tools of GeoPandas with just one line of code. I think that's a really, really big improvement and very exciting. Next, let's just write this data to the Zarr store like we did for the one-dimensional cube. Now we'll just write the two-dimensional cube. I'm not going to go through these steps, but we do just need to follow the same steps that we did the first time, where we encode the shapely geometries as CF geometries. And we need to add in one additional step here, which is rechunking this data set. Zarr expects uniform chunk sizes. And when we perform when we sample the raster data cube at the set of geometries, that can create some irregular chunk sizes. So we just rechunk that and encode those geometries. And you can see that now we have our CF geometries again. We're back to this cube with the geometry dimension and the nodes and a geometry container, which we can see in the attributes. And then I'm just going to write this object to our Zarr store. So I'm going to say vec cube 2D encoded to Zarr repo store. Okay, I'm just going to commit those changes so that we can see them in our repo. Okay, we can come over here. And if we go back, we can see that, so before we were in our cube 1D group, we just created a new group, cube 2D. And we wrote all of those arrays here. So now we have the spatial information and the ERA5 variables. Okay, I mentioned before that it is possible to coerce multidimensional data into a data frame structure, but that it creates some inefficiencies. And I want to just show quickly what that can look like. So we're just gonna compare. We'll make a geodata frame with a time dimension, and then we'll compare the size of that to the two-dimensional vector data cube. So I'll do that by saying GDF long. I'm going to convert this two-dimensional data cube to a geodata frame. So you can see that we now have a geodata frame. It has our atmospheric variables and our time dimension represented here. And we have many rows. We can compute the size of that. Let's just look at it in bytes. So you can see this is pretty small, just under a megabyte. Let's look at the size of the vector data cube. Cool. So our vector cube is less than half the size of the geodata frame. I think as we have larger objects, we can see those gains made even greater. Great, so I'm going to just return back to our slides, but I want to just summarize quickly that in this demonstration, we showed that you can, in addition to reading and writing a one-dimensional vector data cube, we've sampled raster data by a set of vector geometries to form a two-dimensional vector data cube, and then written that, performed some computations and visualizations on that object, and then written that object back to our Zarr store and compared the size of it to representing that same data in a data frame structure. I'm not going to show this in the demo, but I'm not showing this in the demo, but it is important to note that another really cool element of Xvec is that in addition to point geometries, which we just showed, you can also create a vector data cube based on polygon geometries. So you would do this with Xvec's zonal stats method, and that's going to perform a reduction over the surfaces of the polygons that you pass it. This is a repr of that, what that can look like. You can see this is a three-dimensional vector data cube with a geometry dimension made up of an array of shapely polygons. So I mentioned that Xvec is still a relatively new package. This is such an exciting new resource in the community, and it's still under active development. You'll notice a couple rough edges like the plotting that I mentioned, and a couple things with moving metadata around and manually encoding and decoding those geometries. If you're interested in getting involved with this project, I highly recommend you to check out the GitHub repo and raise an issue and start talking to folks over there. And now just to summarize, in this demonstration, we showed that you can connect the raster and the vector data worlds with vector data cubes, and Xvec brings that functionality to Xarray. With Xvec, you can perform spatial queries with Xarray datasets, as well as convert between geodata frames with Xarray datasets, write vector data to Zarr, and copy GeoParquet geometry datasets to Zarr. Thank you everyone for being here today. I want to make a special acknowledgement to all of the contributors and maintainers of the packages that I used in this demo. And then again, the Pangeo community for a lot of really helpful resources. These are some other references that I found particularly helpful, and I would be happy to take any questions or hear any thoughts that folks have now.
All right, looks like we're getting a lot of applause here in the chat. Emma, thank you so much for that amazing webinar. I learned a ton from it. I will take on the responsibility of reading out the questions that people post in the Q&A, and also feel free to raise your hand. We've got our first question from Daniel Yan. Can you elaborate a bit on the magic encode CF performs? I'm especially interested in how it interplays with chunking along the vector geometry coordinate and fetching only subsets of the data from the Zarr store. And I'm happy to also provide some responses here if you'd like.
Awesome. Thanks for that question, Daniel. That's a really good question. And it's something I haven't looked at in detail yet. I might punt that to Deepak or Ryan, who I know have spent a bit more time working on the encoding and decoding step and really how it interplays with the chunking.
Yeah, I can.
Go ahead, Deepak. You got it.
I can try to answer some. I haven't actually tested it, but the magic is fairly simple. It just flattens the whole thing down in order, so it should be possible to do what you want it to do, which is just read the geometries that you want, assuming the chunk sizes line up okay. But I haven't tried it, but I think it should work. Ryan?
Well, I would just add that if you're going to be using the geometry as an index, it has to be fully loaded into memory. That's just how Xarray works. So, chunking can make it more efficient to fetch, but at the end of the day, you're loading the entire list of geometries into memory rather than trying to search through them. And that's a different type of application than if you have like a massive table of millions and millions of geometries that you don't necessarily want to load in. So this is kind of part of the whole theory of data cubes is that each dimension, like the data set may be large, but the hope is that one dimension at least is small enough to fit into memory to create an orthogonal index. If that isn't the case, like I don't think this would scale well to say billions of geometries, right? Because at that point, it's just too expensive to hold all of those geometries in memory, and you would need to use a different solution. But at the end of the day, the actual geometries are just integers, a bunch of integer or floating point numbers. They're just standard numerical arrays. So they can be chunked up however you want and compressed accordingly. And there's also some interesting parallels to between how CF encodes geometries and how Arrow encodes geometries that are interesting to delve into. Probably leave it there for now. So we got a couple more questions in the chat from Soterios. How good is Dask support for vector data cube operations?
That is another one that I have not explicitly tested. So I would hesitate to answer before I have really gone through and done that explicitly. But that's a really good question. I wonder if Deepak or anyone else has thoughts on it.
It's the same as it's as good as Xarray support for Dask.
Cool.
And again, I would just add that caveat that to use Xvec and the whole vector data cube construct, the assumption is that the list of geometries itself is relatively small compared to the full data cube, so that you do load the geometries into memory. And then you can still perform lazy and distributed and chunked operations on the full cube, but the geometries themselves are an in-memory index. Okay, another question here from Michael. What happens when the geometries themselves vary with time? National boundaries change, glaciers move.
Definitely. This is a great question. And I think trying to think about exactly what the structure of this would be, but this is where I think you would need to have essentially your geometries that are linked to a time dimension. And then you could have a geometry dimension that points to that object, but really which exact outline you're using is linked to the time. So I think you'd need to index off of time and then have another index. You'd have maybe a kind of a pointer object that would point to the correct actual geometry. That's how I would first approach doing that. I think it's definitely possible within the Xvec framework, but you would need to be a little bit creative just with how you set up your indexes and basing things off of the time index. If anyone else wants to jump in on that too.
And then, yeah, Maya had basically the same question as Michael, so I'll roll those into one. And then someone had just raised a hand. I don't, who has
yes.
a hand up?
Hi.
Yeah,
Sorry.
Lorena, go ahead.
I don't want
Yes.
to just be the person who says, "Hey, look at my work," but I have been working with polygons that change over time, and I'm implementing that in R. And I'm really excited and looking forward to also make this implementation with Xvec as well. So I will be meeting Martin Fleischmann hopefully in September, and we'll be talking about that. So let's hope that we can stay tuned for some work towards that direction. Yeah, just that. Just stay tuned.
Awesome. Thanks, Lorena. Thanks for chiming in. That's really exciting.
Lorena, if you want to post a link to your project in the chat, go ahead. Oh no, actually, we don't have the ability to do that. The chat is not open. But I would just add, the R community is definitely really ahead on this whole vector data cube front, right? That's really where the first implementation was, and so I'm not surprised, Lorena, to hear that you're making progress on that front. And yeah, in many ways, the Python community is just catching up. So really excited to learn about what you guys are doing and how we can help support it on the Python side.
Cool, thanks. I can try to put it on as a question, but I lost the question pane. But I'll try to make it reachable.
All right, do we have any other questions or oh yeah, new question in the Q&A. All right, let's check it out. Oh, there's a lot of questions here in the Q&A. Okay, Renee asks, as a data provider, how do we set up our data to better be pulled into this type of workflow? Great question.
Yeah, that's a great question. I'll give some thoughts, but I definitely want to hear from others on this who I think have like more experience on that upstream side of things. But I think this workflow that I just showed was relatively smooth. Like there are a couple of things you need to do manually, but really having the data available as Zarr data cubes in object storage and then GeoParquet files in object storage makes this a pretty smooth development. I think we could definitely think about maybe ways of like encoding CF geometries first or something like that. But like I was very pleasantly surprised with like how smoothly we could assemble these cubes here. But Deepak, Joe, Ryan, others, I'd be curious to hear your thoughts.
You know, to me, this question speaks to the sort of data and metadata divide between what I would call like the climate data community and the GIS community. In the climate data community, we have NetCDF and we have CF conventions, and those actually provide a well-constructed way to encode geometry objects. But in the GIS community, it's much more prevalent to use, shapefile, to use, GeoPackage, and recently GeoParquet has really emerged as a great way of storing that data. So, the bottom line is there's good interoperability between all of these different ways of storing data. As a data provider, if you want to provide vector data, I think GeoParquet or GeoPackage, Flat GeoBuff are all good ways to share vector data. If you want to share a vector data cube as a data provider, NetCDF and Zarr can now do that. And that's where a tabular format like GeoParquet would not represent that data in as compact and efficient way. So you can use the approach we showed today to distribute a vector data cube in either NetCDF or Zarr today, and it works. The next question is, should the Xvec package be the way to go when working with vector data in Python ecosystem instead of GeoPandas? I'm going to just take that question because it's one that I feel it requires a really strong and specific answer, which is definitely not, right? Like this work all leverages GeoPandas heavily. The index that Xarray is using is borrowed from GeoPandas. So this would not at all be possible without GeoPandas, just the way Xarray itself depends on pandas for its generic indexing capability. Where the Xvec and the vector data cube approach shines is where you want to bring other dimensions to your vector data analysis. So bringing along a time dimension where you want to fuse that data with raster data. That's where Xvec and the vector data cube approach is valuable, but there's still many, many use cases that benefit from the standard data frame-based approach for vector geometries that GeoPandas represents.
I definitely view Xvec as kind of standing on the shoulders of GeoPandas. So yeah, very, very critical and like still the best way to go in a lot of situations.
Okay, we have an anonymous question. I'm curious about Xvec's extract points functionality. For sampling some points from multiple raster geotiffs, is the speed comparable using raster IO?
I would have to look at that. That's not something I've tested directly. I do know that if you go to the Xvec extract points API, there are different methods that you can choose, and those are some of the trade-offs there, if I'm remembering correctly. So I think there's some flexibility with how that operation is performed, and there's different approaches for different use cases. So yeah, I think I have not done the experimentation there yet.
All right, tons of questions. This is it's always great to have such great feedback. Okay, GUI asks, back to the question on using coordinate as index. Would it make sense a Bloom filter implementation to reduce the index to a subset so it would require to read only a limited number of chunks?
I haven't worked with a Bloom filter before, so maybe someone else can chime in here, but is that trying to get around the requirement that the entire index be explicitly materialized in memory? My sense is that if it were possible, that could be a good way to go about it. I know there's been some work on trying to not explicitly load entire indexes. So I'm not sure kind of all the full implementation of that there. Someone else, please feel free to chime in on that.
Yeah, I mean, my impression is that requires a change to how Xarray works. Xarray doesn't have the concept of a lazily loaded index. Xarray is a weird kind of, you can think about Xarray as a sort of embedded database, right? And its approach is currently to put all of its indexes into memory eagerly. And so it would require a pretty big change in Xarray to take advantage of the approach that GUI is describing here. It's not inconceivable, but it's pretty different from the way things work today. Go ahead, Deepak.
Yeah, I mean, you can imagine not using Xarray, for example, right? If you had this kind of Bloom filter sitting on the side, you could figure out which parts of the data set you did need to read those, then create the index, and you'd be fine. You don't, the creation of the index is separate from reading from data set. You can lazy read, subset down to the geometries you want, as long as you can find them somehow. Then you can create an in-memory index, and then you get all of these benefits. So there's some decoupling possible.
All right, I'm gonna, since time is tight, I'm gonna prioritize the questions that have a couple of upvotes here. So Marty says, hello, I am working with observations from meteorological stations from multiple sources, which may have different resolutions. Vector data cubes would be the natural structure for it. However, is there a way of efficiently using Xvec and Arraylake with Zarr with different time resolutions?
Different time resolutions. So you'd need, my first thought is that I think you would need either individual time dimensions, or you need some kind of way of, again, pointing to the correct elements of one kind of main time dimension for the different sets that have specific time resolutions. I'm just reading the question again.
I mean, I think it's just safe to say no. If the dimensions aren't orthogonal, you can't put them into a data cube using this approach. You maybe can conceptually, but if they have different time, if each point has a different time measurement, it's just not possible to arrange them into this type of data structure. And in that case, you're probably best off either representing them all as separate data frames, or perhaps as part of one data frame where both time and geometry are all rolled up together. But it's not a great fit for the dense data cube approach.
I think you'd essentially be in the situation where you're trying to coerce like multidimensional data into a data frame, and then you're doing querying. It's like, long format, maybe you're wide. And so you're having to kind of account for that in your querying, and it's going to be cumbersome. So I think you'd essentially end up in that situation, like Ryan was describing, unless you had them in separate cubes. Joe?
You're muted, Joe.
Thank you. If you're happy with having separate Xarray datasets, essentially two or more data cubes that each have their own vector geometries and indexes, and obviously time indexes. Xarray is in the process of adding a data tree object, so a more hierarchical object that can have some shared coordinates. And so you could do some of Xarray's logic on two or more nodes in a data tree, which would offer some of the same advantages, but without forcing you to align all of your indexes ahead of time.
Okay, and I think with what will probably be our last question. Joe, you done? Okay. From Ben, your example had a time dimension as the third dimension of your raster cube. Would the process work in exactly the same way for a stack of different raster variables on the same grid with no time dimension?
Yeah, so we could still perform the same sampling. That is similar to the first example where we created the one-dimensional vector data cube that had metadata in those data variables. We could definitely have had raster variables there and just sampled them along that dimension without having a time dimension there. So I think you could still use the extract points on that object to get back to the vector data cube that you want.
Yeah, and I think here you see also a little bit of a divide between sort of the traditional GIS, like Earth observation approach, and then the climate data structure. In Xarray and in NetCDF, we consider those different variables as, is exactly that, a variable. So an Xarray data set naturally holds many variables that share the same coordinates. And in raster world, sometimes those are the only option is band. So, this approach naturally accommodates, many different variables that all share the same coordinates on the same spatial temporal grid. We've reached the end of the hour. I want to thank Emma again. Another round of virtual applause. And I also want to say farewell to Emma. This marks the end of her time here at Earthmover, and I think this has been a fantastic capstone to a great summer. So thank you, Emma. Thank you to all of the attendees. And we are looking forward to connecting with all of you again at our next webinar, which is still TBA.
Great.
Goodbye.
Thanks everyone for coming. Bye.